So this lesson is really about looking at how combining different functions, well, first what it means and some notation for it, but then especially looking at how that affects the domain. And while we can graph things at any time, I want to ideally try to connect it to ideas without having to rely on always graphing things. So just some notation here before I get to the questions. In general, when you're adding or subtracting functions together, you can write it like this. Actually, it should be plus or minus right there. If you're multiplying two functions, this is a slightly faster way of writing it. If you're dividing two functions, this is another way of writing it. All right, that's it. That's just notation, and let's kind of look at this. So what I have here are two functions, f and g. One's a linear function, one we call a rational or reciprocal function. I want to find the equations and domain of the sum, difference, product of these functions. I'm not going to look at the quotient of this yet. And so first, let's look at these functions individually. And if I look at f of x, that's 2x plus 1. That's a linear function. I don't hopefully need to graph this to know that x can be any number. The line goes on forever. And so the domain of this is all real numbers. And there's many ways of writing it. I'll just say this. X belongs to all real numbers. If I look at g of x, I have this. And this function we're surely less familiar with than a linear function. You could graph it and see that there is a break. X can't be anything. Or you can inspect the equation and realize if x is -5, we're dividing by 0, and division by 0 does not make sense. And so other than that, x can be anything. But as long as x is not -5, this function's okay. But x cannot be -5. And so the domain is everything but -5. And there's several ways of writing it. It's the way I prefer. It's just to say x cannot equal -5. You can use other things. For example, if you want to make it sound more cumbersome, you could say it's the union from -infinity to -5, not including -5, and then have this symbol here, which means the union, kind of like as well as -5 up to +infinity. These mean the same thing. I definitely like this one better. No offense to the bottom one. And so I got the domain of g and the domain of f. All right, I want the equations for the sum, difference, and product. So we'll talk about quotient later. And so the sum of these, which I can write as f plus g of x. The equation is just simply 2x plus 1 plus g of x, 1 over x plus 5. There's the equation. I don't need to do any more than that. The domain of this is going to be the same as the domain of f and g in terms of what they have in common. So anytime you add or subtract or multiply functions together, the domain you get when you put it all together is the same as what the domain of what they have in common. And so if I look at f of x, the domain is everything, absolutely everything. The domain of g of x is everything but -5. So what do they have in common? Well, what they have in common is everything but -5, because this includes absolutely everything for f, and this is almost everything for g, just not -5. And so what they have in common is everything but -5, which again, I could write as I did before here, but I prefer just saying x does not equal -5. You could then say, other than that, x belongs to all the real numbers as long as it's not -5, but we're good enough. And when you subtract, you're going to get the same thing. And so f minus g of x. The equation will look different. The function will behave differently. It's -1 over x plus 5, but the domain will be the same. And same thing when we multiply. If we had f times g of x, this is a different function. It looks very different if you were to graph it than what we had before. Which I could, in this case, write as 2x plus 1 over x plus 5, if I just put these together. However, that doesn't really matter in terms of my domain. The domain of this, again, will be everything but -5, because everything but -5 is what f and g have in common. I'll quickly switch to decimals here, just give you a visual, although again, this is all we need, but it's never a bad idea. And so just for some graphs, I know all of these should have the same domain, they'll be different. So this is f plus g. Notice it's everything but -5. And you may, in fact, actually, I shouldn't zoom out yet. It may look like the function doesn't exist when it's less than -5, but if I zoom out, yeah, it does. We always want to adjust our window settings. Here's a different function. This is f minus g. It looks distinctly different, but again, there's this break right at -5. And then this is when I multiply them together. Distinctly different function, but again, there's this break at -5. Later on, we'll talk about what this break is called. It's called a vertical asymptote, but the key is the function breaks apart. It doesn't exist at -5, which I could see algebraically from right here. All right, so next I want to focus on some different functions and eventually getting to quotients, because quotients, which means we're dividing them, we got to be a little bit more careful. But first, same idea as before. Here's f of x. It's the square root of x. And again, you can graph things anytime you want, but we've long ago learned that the square root of a negative number is not a real number. And in general, if you're dealing with real numbers, there is no square root of a negative number. And so we're dealing with real numbers, and so the domain is anything greater than or equal to 0. You can find the square root of 0, but once it's less than 0, it's not a real number anymore. And for the time being, that's all we're dealing with. And so for g of x, I have x minus 2 over x plus 5. Again, you can graph this. But what you'll see about your graph is there's a break. And the break for this graph is when x equals -5. For the same reason as we saw in the last question, we can see right here. When we're dealing with division, you can't divide by a negative, and I can just see by analyzing this or by inspecting this that when x is -5, my denominator will be 0. And so, but everything else is okay. You can, 0 is cool in the numerator. 0 divided by anything is okay. You just can't divide. So 0 divided by anything is okay. You can't divide by 0. You can't break things up into groups of no sizes at all. But keep in mind, if you have like 0 divided by 5, that's okay. One way of thinking about that is you have nothing, and you break it up into 5 groups. Each group has nothing. That's okay. But the other way around does not make sense. 5 divided by 0. You have 5 things, and you want to break it up into groups of 0 size, or you want to break it up into absolutely no groups at all. That's just not possible. Either way, the domain of this is x does not equal -5. And like before, you could write it in different ways. All right, so when it comes to finding the domain of the sum, the difference, and the product, these first 3, I'm not asking for the equations. They're all going to have the same domain, because whether we add, subtract, or multiply these functions together, their collective domain will be what they have in common. And so first, let me just kind of write this out. So the domain of whether I look at f plus g of x, and I look at f minus g of x, or I look at the f times g of x, all of these will have the same domain, are all, and it's going to be what these have in common. So now let's look at this. The domain of root x is everything greater than or equal to 0, so all the positive numbers as well as 0. The domain of g of x is everything but -5. So what do they have in common? Well, really, just this. The x cannot equal -5 doesn't matter for any of these when we put the functions together, because the domain is what they have in common, and which means right here I have everything greater than 0, which means anything less than 0 is automatically not going to work, because as soon as x is less than 0, my f of x function becomes non-real. And so I don't really have to worry about this anymore, because that already is less than 0. It's kind of like saying, if we included this as well, that would be a bit of a problem, because then we're saying x has to be greater than 0 or equal to 0. Oh, and as well, it can't equal -5. Well, of course it can't. We already said it has to be greater than or equal to 0. So in the end, all I need to say, and all I should say, is that the domain is where x is greater than or equal to 0. Now, before I go on to the quotients, let me just switch the Desmos here. And let me show you these 3 graphs. They're all different. But notice all of them start at 0 on the x, and then they just go on and on and on, even though they're all different. So now let me look at these quotients. I have 2, f divided by g, and then g divided by f. Let's start with f divided by g. So f over g of x. So in terms of an equation, which I don't have to write down, but I will, that's root x over g, which is a fraction itself, x minus 2 over x plus 5. Now, while it's okay to leave it like this, anytime we have a fraction inside a fraction, we can always simplify it down to a single numerator and a single denominator, just using a little bit of middle school math. So keep in mind, when I'm dividing with fractions, dividing with anything, I can think of this as root x times, instead of dividing by x minus 2 over x minus 5, I can think of it as times the reciprocal, x minus 5 over x minus 2. Which really, all I need is one single fraction. I can say root x times x minus 5 over x minus 2. Keep in mind, I never actually needed the equation here, but it also wasn't terribly hard. So what's the domain of this? Well, it's going to be this, as well as, so I'll kind of write this down. So the domain of this is x, it must be greater than or equal to 0. But now I have a bit more to think about, because as soon as I'm dividing by g of x, I also have to make sure g of x doesn't equal 0. I'll also have to make sure this was g of x. This does not equal 0, because anywhere that this denominator, x minus 2 over x minus 5, which is the denominator is a fraction itself, anytime this function equals 0, I'm dividing by 0 from this big fraction. Fractions inside fractions. And so where does x minus 2 over x minus 5 equal 0? Well, you could graph x minus 2 over x minus 5 and just see where the output is 0. Or just realize that if I have a fraction here, the only way a fraction of x minus 2 over x minus 5 can equal 0 is if my denominator equals 0. The only way, oh, here we got an announcement.
Justin Bailey, if you are in the building, please report to the office. Justin Bailey, if you are in the building, please report to the office. You have left an item in the office.
Oh, Justin. Justin. All right, the only way this can equal 0 is if my numerator equals a 0. If that numerator equals a 0, then I'll have 0 divided by something else, and that will automatically equal 0. So really, to make x minus 2 over x minus 5 equal to 0, all I really have to do is think about what makes x minus 2 equal to 0. Well, that's if x equals 2. And so if x equals 2, x minus 2 over x minus 5 equals 0. And you can double check if you want. But right here, if x equals 2, then all of this equals 0. Well, remember, for the domain, I can't allow this whole part to be 0. If this whole part in blue equals 0, I'm dividing by 0, which means x equals 2 is something as well that cannot be part of this. So in the end, my domain, I have to add something. It's everything greater than or equal to 0, and x cannot equal 2, which you can write in a variety of ways. I can also write it as square bracket 0, comma 2, round bracket, the union of 2 up to infinity. But again, I kind of prefer that first part. As well, though, everything I just described, you can also kind of see in this last step. If you look at this last step, I can see right there that if I simplify it, I'm dividing by x minus 2. And that's another way of realizing, yeah, x cannot equal 2. It makes it a little more explicit that I will be dividing by 0. With that said, let me show the last one, which is g over f. Which is x minus 2 over x minus 5 all over the square root of x. Again, I could simplify this. I'll just leave it like this for now. And so again, the domain of this will be the domain of what f and g have in common, which we've seen several times, is x is greater than or equal to 0. However, now I got to look down here, and this cannot equal 0. So I got to think, when will the square root of x equal 0? Well, I can just tell by inspection. The square root of x will equal 0 when x equals 0, which means another part of my domain is x cannot equal 0. Now, if I leave it like this, that's a little bit silly, because I'm saying first that the domain is greater than or equal to 0, and then I say, oh, actually, no, it can't be 0. So a much more concise way of saying this is just to get rid of that little bar under the greater than symbol. X must be greater than 0, nothing else. There we go. That's the most concise way. And if I go to Desmos here and turn these off and show you f over g, this is the one we saw that especially if I adjust my settings, you can see, yep, x starts, it goes from 0 up, but when x is 2, there's a break in my graph. We kind of noticed that before. This is the one I was just working on. Notice there's no break at 2, but it never actually reaches 0. And again, if I zoom in, it's not quite touching the y-axis. And again, we'll learn that's called an asymptote later on. But notice I never really needed to use Desmos. It does do a nice job of visualizing these. Last one, I have the graph of two functions. I have f of x, which is root x, which must be the one in red. And I'll label it this. And I have g of x, which must be the one in blue. All right, on the same grid, I want to sketch a graph of f minus g of x. Now we have a few options. First, let's think about what this means. Here's f of x, here's g of x. And so f minus g of x would look like root x minus x plus 6. A lot of negatives there. And those brackets are essential because I'm subtracting all of that, which cleans up to root x plus x minus 6. All right, that's the function we're looking at. And again, it's not wrong at all to go into a graphing device and graph this. However, I also want to point out something that's fairly pleasant, is that if you're just subtracting these two functions, if I'm subtracting f take away g, that means another way of visualizing it is I can just look at the graph and take my y-coordinates and subtract the y-coordinates of, in that order, f minus g. What do I mean by that? Well, let's look at my graph. So here's f in red, g in blue. If I look at f in red, the y-coordinate at the start is 0. At that same point, when x is 0, g of x is at 6. And so the y-coordinate of f minus g is going to be the same as 0 take away 6, which is negative 6. So I know, without even graphing anything, this combined function must start down here. I also know it must start there because, again, even though my line goes on and on and on forever, when I combine these functions together, I only look at what they have in common. And since my f of x only starts at 0, root x only starts at 0, my combined graph has to start at 0 as well. And I can do the same thing for all these points. If I look at this point right here, the y-coordinate is 1. Compare that for the same value of x up here. The y-coordinate is 5. And so I'm subtracting f minus g, so it's 1 minus 5, which is negative 4. So I know my graph must go through this point here. Carried on for a couple more points. Right there, f and g have the exact same coordinate for their output, for their y. They're both at 2. 2 minus 2 is 0, so f minus g must have a y-coordinate of 0 at this point. And lastly, right here, this has an a y-coordinate of 3. If I look in the same spot in the x down here, this has a y-coordinate of negative 3. And so if I go 3 take away negative 3, that's the same as 3 plus 3, which is 6. And so when x is 9, as I can see, my graph must be up here at 6. And I can now get a pretty good idea what this graph must look like. It must look almost like a line, but not quite. A ruler won't quite go through all these points. And again, it starts right down there at the bottom. Because again, without even graphing anything, I know that when I combine f and g together, their domain will be what they have in common. One goes on forever, the line. One only starts at 0 and goes up. So what do they have in common? 0 and up. And if you go to Desmos, maybe I'll just show you quickly, you'll see a pretty darn similar thing. And so let's graph that here. Y equals root x plus x. Oh, make sure I type it properly. Plus x minus 6. Adjust my zoom settings, and I typed that in wrong. Plus x minus 6. There we go. And notice what I have here is pretty similar to what I sketched right here.